All right, it's me and then lunch, right? And much more excited to see me than lunch. That's great. I was sitting with Yanni and Matt last year at the Q2B conference, and one of the things we did with them is kind of share what Honeywell is doing in this space. And many of you may not know really what we're doing in this space, but it's been quite a long time coming, and as we had that conversation with Yanni and Matt, they said, why aren't you presenting? Like, why don't you tell people what we're doing? So we are. So today, I'm going to talk a little bit about what we're doing and why we're doing it. And I'm going to start with why Honeywell is in this space. So you may have heard the brand, but you may not know exactly what it is we do. So I'll start there. What do we do? Honeywell Products, Honeywell Systems, subsystems have been on every human space flight that NASA has launched for the last 6 decades. Honeywell Systems are on 80% of all satellites. Who flew here? Who flew to the conference? Raise your hand if you flew to the conference. Okay. Raise your hand if you flew on a private jet. All right. I was trying to look for a way home, but okay. Assuming you're also going to fly back, then you have a nearly 100% chance you had Honeywell products on your plane. We have the avionics in the cockpit. We make the wheels and brakes. We make the APUs, the auxiliary power units that power the plane while it's on the ground. We actually make the satellite internet connection. And we make the black boxes. So we make a lot of these products that exist in a segment like aerospace. We are also have products in 17 million buildings around the world, from integrated security and fire systems to building control systems to energy efficiency solutions that have the ability to reduce energy consumption by as much as 20%. We are in 95% of all petrochemical refining plants in the world. We make these big distributed control systems that control that full operation, as well as making the safety equipment that is necessary for hearing protection, for fall protection. We make gas detection so that you can be alerted if there's a hazardous situation. And when you make all of those things, it turns out you make a lot of the industrial Internet of Things. So we take the data, we take those assets, and we bring them back, and we do computation that helps do optimization, that helps do real-time management of control of some of the most complex systems on the planet. That's actually what Honeywell does. Now, how do we do that? Turns out that there are a lot of underlying technologies that enable us to do all of those things. And that enabling technology, turns out it's foundational to quantum computing. So about a decade ago, I had a couple of geniuses come to me, and as they walked through this litany of, hey, did you know that we do ultra-high vacuum? In fact, we make ultra-high vacuums that are the size of a penny. We do lasers and optics for ring laser gyros, for being able to do terrestrial and non-terrestrial communication. We do cryogenics that allow us to do gas sequestration, and we do cryogenics that allow for cryo coolers for things like large telescopes. We do these big Spirion Orion control systems that allow us to do complex controls of petrochemical plants, but also do the onboard control of fighter jets. We may have our own foundry to make a lot of the MEMS and integrated circuit technologies that go into these products. We do all the RF signaling that allows us to connect products from one to another, as well as large and small magnetic sensors that allow us to actually manipulate a lot of the electric fields, magnetic fields that go into our offerings. And they said to me, do you know what you can do if you put all that together? And I said, of course not, because I'm an engineer, I'm not a scientist. And they said, well, you can build a quantum computer. And I said, that's awesome. So we had a conversation with the CEO of Honeywell and said, you know, if we took all this stuff and put it together, you know what we could do? And so we started investing. We already did this technology anyway, so let's go continue to do that, but then let's start bringing it together. Let's start putting a little bit of investment in place and see, are we really good at this? Can we be good at this? Turns out we can be. So about 4 years ago, we said we're going to go and make a very deliberate, very strategic decision to build up a capability for doing quantum computing hardware development. Now, any strategy involves nouns. That's it, nouns, people, places, things. So what do? We said, okay, we're going to have to go build one of the most capable teams on the planet for quantum computing. We need to make sure that we have the assets in place to be able to go and do that work. We need to buy all the equipment to be able to do that. And we did all of that under the radar, intentionally, right? Why did we do it like that? Well, we wanted to do here's what it really does. Here is what a quantum computer looks like instead of doing PowerPoint. And so we very deliberately, very strategically built up this team, some of the most capable quantum scientists in the world, and then we surrounded that with what Honeywell does really well. All of the software developers and engineers, systems engineering, multidisciplinary, electrical engineering, mechanical engineering, and all of the rest of the business infrastructure to build an at-scale team. Because our belief was, this is not a science project for us. This is going to be a business, and it's going to be a business for us because our businesses are going to be profoundly impacted by quantum computing. We believe that. And since we believe that, we said, let's build ourselves at scale so we're tackling this in the right way. All right. So our approach. We actually had a choice. So going back a decade ago, we looked at those technologies and we said, what do we want to go do as a company? How do we want to approach it? And our approach was to use trapped ion as the underlying technology. Why? Well, one, we have our own foundry, so we can make our own traps, and we do. So we start with the architecture and we build everything up from that. Then we had to develop bespoke control systems. As much of a controls expert as we are as a company, we didn't have what we were going to need in terms of the timing, the speed, the precision necessary to go do quantum computing, so we built from the ground up bespoke control system. Then we knew we were going to eventually need cryogenics. Yes, trapped ion has a fabulous ability to be able to do quantum computing at room temperature. There are benefits you get if you start to cool that down. And so we said, we're going to do this right away because we're going to take advantage of those benefits in the early days. Then we said, okay, if we really want to make this difficult for ourselves, let's tackle some really tough things, and let's do it now. Let's do it first. What are some of those tough things? We wanted to be able to move the qubits around. Because when you start to think about scalability, you're going to need to think about things like transport. So we started doing transport. We wanted to make sure that we were going after the highest fidelity gates possible. And we wanted to be able to do things as quickly as you can with trapped ion as the underlying technology. To do that, we did something called parallel operations. What does that mean? That means our traps have multiple gate zones so that we can do operations on 2-qubit pairs all simultaneously as you go through the circuit. Now, what does a quantum computer look like? You've seen pictures of other people's quantum computers. Oftentimes you're looking at a dilution refrigerator. But there's a couple of things that are going to be consistent, which is the magic happens on something about the size of a postage stamp, regardless of the technology, and you have to have a whole bunch of infrastructure around to make that work. And what that ends up usually being is things like the cryogenic application. So for us, if you look at those red dots in the middle there, it all starts with our physics package, something about the size of a basketball. We have an ultra-high vacuum around that. It's about 5 times less particles in outer space. And if you think about that and put your hands together as a little kind of ball like that, in your hands is roughly 1 trillion atoms, just in your hands. We want to deal with one at a time. So you have to pump all the rest of that beautiful set of atoms out, which is why the ultra-high vacuum. You cryogenically cool it down, which for us allows us to get even better vacuum, allows us to get longer coherence times and longer duration circuits. And then you wrap it with a control system that allows you to do real-time operations of the circuits as you run them. Why is that important? It's important because one of the beautiful things about trapped ion is that you're starting with something that is perfect, given to you by the universe, given to you by Mother Nature. And so you take that, and then every error is something you've introduced. So once you start with that perfect qubit, you can wrap it around with a bunch of things, and you better know what is causing your error. And one of the beautiful things about trapped ion is you can have a long, you might be 12 sets of variables, but you know what is introducing error into your system, and you can put in place something to mitigate each one. And by doing that, the real secret is that precise control, that precise manipulation of the qubits. So I'm going to show you a little bit of how ours works. It starts with a trap, and you atomize, in this case, ytterbium gets put into the trap, and then you need to turn it into an ion. So how do you do that? You hit it with a laser. Once you hit it with the laser, you photoionized it, you give it a charge, and now I have the ability to manipulate it. So those gray lines you see on there are RF rails, and you can create a potential well. You create a little field around that qubit, and then you can start to move it. How do you move it? You have DC electrodes that go up and down. That's what those little square boxes are. DC electrodes that we've populated throughout the trap, and then you create RF waveforms to be able to make little waves that move your ion around. You put it into a gate zone, hit it with another laser, and now you've imparted quantum information. That is how you start with a single qubit. Okay, well, what if you have more? Then you just load in multiple qubits. What do? You put them together in the same potential well, again using RF signals. You put them in the same zone, you hit them with perpendicular lasers, and now you have done a 2-qubit gate of your system. So, okay, Tony, great. You did a PowerPoint animation of qubits working. Yeah. Okay, would you like to see it? Would you actually like to see how it works? Okay. As a setup, remember atoms. Tiny atoms, right? From Earth to a baseball is about the same as a baseball to an atom. So, going to be a little pixely, not going to lie, the video a little pixelated. And what you're going to see is you're going to see 2 ytterbium atoms start together. We're going to separate them out into different zones. We're going to shift one back. We're going to shift it out. We're going to shift both at the same time. We're going to take that other one and shift it in, shift it out. It's a little dance. It's a quantum atom choreography, and we're going to bring it back together. That's what we're going to do. So here you go. Okay, honestly, I thought there'd be some clapping. Maybe I'm gonna do this one more time. You have to pay really, really fast attention. Okay. There you go, perfect. I'll help you out. I'll tell you what, I appreciate the pity applause. I'm gonna help you out. I'm gonna slow it down about 1,000 times. It's like, like Matt showed earlier, imagine an American football play where you had to watch it in such super slow motion that it would take an hour or 8 hours to watch. That's what we're gonna do here. So here you go. So why is that so important? Well, if you think about the way this is going to need to work, the way trapped ion is going to need to scale, one of our strategies, and it's been talked about before, is being able to use something that allows you to move these ions around, move these qubits around. In our case, the primitive motions to be able to do that are split, combine, shift, and swap. And that is how it works. Is it hard? Of course it's hard. It's taken a lot of effort to be able to get the control systems in place to be able to go do it. Again, designing the trap from the ground up, the architecture from the ground up to be able to be in a place to be able to execute on that. And so here we are. We are at the point where we are starting to release our first commercial quantum computer. We have the benefit of an all-to-all connectivity. We have the benefit of very high fidelity gates. We have the benefit of having numerous qubits. But what if you were also a controls expert? What if you had that? What would you do? Well, one of the things you might do is something that we call measurement condition branching. What does that mean? That means pressing pause in the middle of a circuit, saying, I want to know what that qubit is right now. I'm going to stop the computation. I'm going to grab that qubit. I'm going to say, are you a 1 or are you a 0 right now? And depending upon that answer, I'm going to make a different decision. That's what we've done with measurement condition branching. It's the equivalent of having an if statement in quantum algorithm development. Now, what if you could have such long coherence time that not only could you have a pre-planned set of things that you'd go do if that happened, but you could run that through your classical computation, come back with a result, and then change your answer of what you would go do with the rest of the circuit. That's what we've done. What if you had such precise expertise and you had such precise control over the single qubit that you could have rotation that was basically arbitrary, pi over 500 set of rotations for the single qubit. That is the kind of power that you can bring when you combine that controls expertise with trapped ion technology. And then, what if you had a set of theorists who knew that this was coming, could plan for this, and say, how can I take advantage of these things that just haven't existed yet, but I know is coming? Well, this is my trailer for Dr. Mike Phosphate, who's going to be presenting tomorrow in the D, I guess, track D. They did something very cool, which is if you decide you can take that selective mid-circuit measurement, there's a way to do, my words, not Dr. Phosphate's words, a compression that allows you to take smaller size systems and simulate much, much larger systems. This is the kind of power that you can bring when you have the combination of the technology that underpins it, the controls expertise, and the theory team on top of that. So we always get asked about scaling. So this is our strategy. Is it a good one? I hope so. Somebody won a Nobel Prize on it. The challenge is, how do you go do that, right? Well, it's been around for a while. Why hasn't anyone done that yet? Because it's hard. It is hard. But what does it take? Well, it takes being able to control your own trap architecture. It takes being able to move your qubits around, transport them around. It takes the ability to have the longer coherence times, the good fidelity gating, and it takes being able to start with things like this. So we are on our 4th generation of trap. We have a set of cascading offerings that we're planning to bring to the market. This is an example, we call it our H-trap, of being able to demonstrate the motion that you need to be able to do that QCCD type of architecture, be able to turn corners. So we have 7 quantum systems working right now. We are about to bring one out to market commercially. One of our 7 is this setup, as our team is going and putting in the waveforms necessary to go do that junction transport. You're going to be a little bit disappointed in this, only because you're going to say, all right, tell me what? Tell me how much? Tell me when it... not going to do that. So who knows? Who does know? Well, clearly Microsoft knows, and we are very proud and happy to be a partner of Microsoft's in this Microsoft Azure Quantum. And our other enterprise partners know as well. And we've been very deliberate about that. There are people that we are working with right now in our beta phase collaboration that have early access, and our plan is to then roll this out more publicly and commercially in the first half of next year. So I'm excited to be able to share that with you. We will continue to share more information now as we're kind of coming out from hiding and being able to demonstrate what we can actually do. And I'm happy for you folks to be able to come and see us in our booth. So thank you very much. Question? If your question is how many qubits, I'm not telling you.
No.
Do you have a private jet? Okay.
Thanks for powering mine. But so, having joined the field more recently than the other quantum computer makers, what was the biggest drawback, and how did you overcome that?
Great question. The first is just kind of awareness. So we have been doing this for a long time. For a decade, we've been kind of planning this. For the last 4 years, it's been a dedicated business that I have had the privilege of running to be able to go and put this together. So it's more starting to now expose it to the world that it exists. And that has only happened really in about the last 10 months. And what we have seen, and unfortunately they're under NDA, so they're probably not going to be able to tell you, but what I will say on their behalf is the people that we have as our channel partners in this, as our enterprise partners, when they come and see, which is what we do, we say, let's not talk about this, let's just fly into Boulder, it's a beautiful area anyway, come see our site, and when you walk in and see what we've done, it blows people away. So we're kind of at that point now where we have to start obviously making it a bit more public to the world, and we're excited to do that. Question back there?
Yeah, I was kind of curious about your mid-computation branch analysis that you guys are doing. In order to not collapse the wave function, I was curious if you encountered the no cloning theorem problem, and I was wondering if you guys have like dedicated ancillary qubits or something to try to be able to analyze a state mid-computation without collapsing the wave function?
You're probably going to get a better answer by coming to our booth and talking to some of our physicists. I will answer it this way, which is we don't. We actually do not have ancillary qubits that we need to be able to go do that. One of the ways we do develop our system is that every qubit that is carrying information has a buddy qubit of another species, and we do that so that we can cool that and sympathetically cool the entire chain down. And the way we have set up the trap itself allows for enough spacing to be able to go do individual interrogation and be able to do that kind of measurement and then take the measurement condition branching action. But you're probably going to want a deeper physics answer, and you're going to have to go to my team for that one. Any other questions?
Yes, thank you for a nice talk. I was curious about your plans on integrated photonics. I saw it in the last slide. Can you elaborate?
Sure. For any technology is going to have scaling challenges. Ideally, people have already thought through what those are, right? And then you say, okay, it falls into 10 different categories. For us, it falls into 11 different categories. And so for each one of those, we have already teams and work going on to be able to go and cross those hurdles. That's one of them. So are we doing work on having integrated photonics? Of course we have work going on to do integrated photonics. I shouldn't say of course. But we are, yes, we are doing that. And it falls into categories like How are you getting the beams in? How are you getting the readout? You know, what control system changes do you have to have when you're having not just tens or hundreds, but thousands of qubits that you're interacting at once? And so each of those, like I said, 11 different areas, we have ongoing development programs for.